So someone just ran into class huffing and puffing, and I thought I'd just give to all of you some advice for how to, more important, how to leave a class or a talk. It's like incredibly boring. So you don't like skulk out. What you do is you like lift your cell phone to your ear or look at your watch or something and run out really fast. Like, there's someone I met at a conference who kept doing that at every talk, and it looks really convincing. It looks like you've got some real need to escape. To do something very useful. So if you're going to get bored, just do that. Okay. So today I'm going to be talking about this concept of flags for finite sets and for finite-dimensional vector spaces, or if you prefer, projective spaces. And so let me just remind you about that. So it goes all the way from here to the blue line.
Yes, that's right.
So we have over here the world of finite sets, and then over here the world of finite-dimensional vector spaces. And if you like, you could glamorize it all a little bit and say that over here we're going to talk about set theory. Limited aspects of set theory. Over here, we're going to talk about projective geometry, actually. And we're going to see a huge analogy between the two. And the idea is, in simple terms, that here we have our favorite n-element set that we just call n. Over here, we have our favorite n-dimensional vector space that we just call f to the n. F is our field. And so, for example, over here, we have, say, n equals 3, the 3-element set. Over here, we have a 3-dimensional vector space. But what we do over here is we're always interested in subspaces of this, the geometry of subspaces of this. So what we're really doing is doing projective geometry. So we have lines through the origin, so 1D subspaces in here, in this vector space. They're going to be what we're going to focus on and call them the points of the projective space. And so this n equals 3 example here that I'm drawing, over here it really corresponds to the projective plane. So I can draw it on the blackboard. And one of the features of a projective plane that makes projective geometry so nice is that if you have any two distinct points, there's a unique line through it. In particular, if you have 3 points that are all distinct, you get these lines here, and dually, any pair of distinct lines intersects in a point. So the analogy is supposed to be that over here, we're thinking about this 3-element set. Over here, there are lots of pictures like this that you draw on the projective plane, but any one of them, any one of these pictures, which I guess is called an apartment, technically, looks a bit like this. And in particular, we can sort of imagine that even though we're doing set theory here, that we have a concept of a point and also a concept of a line. So I can draw this kind of line here, but it only contains 2 points. And then we have this thing that's sort of like a baby projective plane that contains just 3 points. So here a line. And here a line is just 2 points. Whereas here a line is an honest, full-fledged line. So maybe you can probably make it look. And so what we are going to do is think about the concept of a flag in both situations. So over here we have points, pairs, triples, and so on. Pairs of points, triples of points. Over here we have points, lines, planes, and so on. And a flag is a collection of such things, and a certain, each one is included in the next one, but more precisely, so a D flag in N, the N element set, is just something like this. It's a bunch of nested subsets, let's say K of them, where the smallest one is just the empty set, and the last one, the biggest one, is your whole set, your whole N element set. Where what we're doing here is we're picking an uncombed Young diagram, D, for example, like this. And what's that? Well, it's just a list of numbers that adds up to N. And we're using that to say how big each of these subsets is. So the idea is the ith one minus the I minus first one has size n sub I. So we're regulating the sizes of these sequence of nested sets. And then over here, we have the same concept in this projective geometry guide. So a D flag in, I think I'll describe it using vector space language, so I'll say the vector space is subspaces of that vector space, starting from the zero-dimensional subspace and going on up to the whole n-dimensional vector space, where so D is as before, I go to uncombed n-box Young diagram. And then now, it's the sizes of these quotient spaces of one space mod the one before it that has dimension given by the numbers n1, n2, and so on. Okay, so that's what I talked about last time. I know I haven't been around for a while, I've probably forgotten who I am, but that's what I said. So what I want to do now is I want to just count some of these kind of things, and I want to do the homework exercise that I gave in the first class. So the homework exercise was just to count the number of D flags in Fn, and count the number of D flags in N, and see how they're related. When F, the field, is a field of Q elements. And then the marvelous thing that happens is that when Q, the number of elements in your field, approaches 1, the number of D flags in Fn approaches the number of D flags in N. Of course, it's sort of weird to say that a prime power approaches 1, but you can write down the formulas and then see what happens as Q approaches 1. So I want you to do this. So I'm going to do it in sort of the form of sequence of doable steps. So we're going to start out with easy ones. And we'll see a bunch of stuff. So we'll count the D flags in N and also F to the N, where F is the finite field of Q elements. So let's start out with some easy Young diagram of D and then work our way up. So let's start out with D being a Young diagram that looks like this. I think that's the easiest non-trivial kind. So here, N1 is just 1, and N2 is the rest. So it's N minus 1. So remember, I use the symbol D of N to being the set of D flags on the N element set. So let's just count those for starters. D flags on N. How many D flags are there on the N element set for this kind of D here? Well, maybe I should ask it this way. What is another name, a less complicated sounding name for a D flag on an N element set in this particular case?
The one-dimensional space contained by an
I want to do the combinatorial case, not the vector space case. You would be right if you were talking about this case, but we're going to do this case always right before we do this case. This case is actually sort of easier.
Pointer set.
So what?
Pointer set.
Pointer set?
Pointer set. Set is a special distinguished space.
That's what you call a set together with a D flag of this type. That's right. But what if you just had the set N? What would you call a D flag on it?
A point?
You fix an N. A point. That's the word. A point. Yeah. So a D flag on N is a fancy name for a point. Right? So this guy is special. He's the point, and then there's just like all the rest of them. So this is just the fancy name for the set of points of N in this particular case. And so what's the answer? N. Okay. As I said, it's going to start out easy. Okay. So we now have to count the number of points in an N element set. That's the first lesson in combinatorics. So, and that's what we're doing here. We're doing combinatorics. We're not going to impress any combinatorics for a little while, that's for sure. So, okay. So that was fine and dandy. Sorry, I'm just torturing you, Prasad. Pretending like I'm going to go over to the next panel, but not really. So let's count these. But again, before we count them, we should know what they are. So what's a fancy, what's a nice name for an element, for a D flag on S to the N, where D is this kind of thing? A one-dimensional subspace of S to the N, or the line, the origin, I guess you want to be careful. Or if you're talking projective geometry, it's called a point. Yeah, okay, so these are called points again, but these are points of the projective space. That's just different names for the same thing. Okay, so now how many points are there in the projective space? When our field, of course, you have to know how big the field is. The field has Q elements. So we did this already, but I just want you to remind. How many points are there in the projective space of the n-dimensional projective space?
N.
Sorry, the n-dimensional projectivization of the n-dimensional vector space.
N.
Okay,
Inside.
you're laughing, but he's saying it's n inside. Well, yeah, it's called n sub q, but I want to know what it really. That's just a notation.
Q to the N minus 1 over Q minus 1.
Right, so there's different ways to think about this. The way I really like to think about this is, so this is called a Q integer, the nth Q integer. So we've just taken this formula here, and we've modified it, but in a way that reduces back to the original 1 as Q approaches 1. Notice this approaches n as Q approaches 1. But what's the real meaning of this thing? So what is Q to the n minus 1 counting? The number of points in, not quite in F to the n.
Fn star.
F to the n minus the origin.
Oh, so that's minus 1, right?
Well, 1 is the set consisting of one thing, which could be called 0.
Well, I thought you asked you to take it.
Oh, I'm sorry. No, I was asking what the, yeah, you were just telling me the answer to the first part, but I want to know. So, right, so in other words, we're describing lines through the origin in F to the N. You would say, well, to describe one of them, I can pick any non-zero vector and draw the line through that. So this is the non-zero vectors. And then we're doing what? We're modding out by rescaling. So what are we modding out by?
Non-zero elements of F.
Yeah, the non-zero elements of F, the invertible elements of F, if you call it F star, if you want to show off, right? So this thing here is just the projective space, right? That's what the projective space is. And so the point is that should make it seem really believable, or almost hilarious, in fact, that when you count it, you get the exact same formula, but with just the numbers here replacing the things with the numbers of.
So that's not for any Q. I mean, any integer or any prime.
So Q isn't an integer. Well, Q is an integer. This whole thing is called a Q integer.
Yeah, I mean, but Q is.
Q is any integer that there's a field with that many elements of, any prime power. It's a unique field with any prime power of elements. And so for some reason the case Q equals 1, it's different from all the rest, but it's sort of like learning to be a prime power just like everybody else, and all the primes to be 0, right? So that's the limiting concept here. But the point I'm trying to make here is that this is a perfect example of what we call decategorification. Namely, in math, we think we're talking about the numbers, but the numbers often are really the numbers of elements of some set. And we wrote in combinatorics, what we do is we take sets and turn them into numbers by counting them. That's called decategorification. It's an example of decategorification, because we're taking the category of finite sets, looking at isomorphism of classes of finite sets, numbers, and just working with those, in other words, counting. Of course, what we sort of would like to do is go the other way. In other words, take formulas that people worked out and realize, hey, you don't need to just talk about the numbers, you can actually talk about the set. You can always, it's easy to slide downhill because of that, but it's just better to stay up on top of the hill and actually work with the sets. So the Q integer is really just sort of another way to say what they are, is just the decategorified versions of these projective spaces. They're just the projective spaces. Or just a number of elements of the projective spaces. So that's the decategorification. Okay, so that was that, and you notice that indeed as Q goes to 1, this is an ordinary integer. Now let me do a slightly different flag, slightly different kind of flag. So now, let's try something a little bit more ambitious. Let's just do this particular one for starters here. Let's say n1 is 2, and n2 is 3, so n is 5. So this, a D flag on a 5-element set is something or other. So this is the D here. So what is a D flag on a 5-element set? Don't give me a more or less snappy name for what it is. It's not going to be just kind of be this point.
There.
That's a little big.
Exactly the point.
There's a subspace.
Is it an ordered pair?
Uh-huh.
No. So you have to be careful, because people, when they take pair, they almost always mean ordered pair. There's so much that if you take pair, they don't.
Unordered.
Yeah, so unordered pair, or 2-element subset. Yeah, that's right. So D flag on 5 are the 2-element subsets of 5. So how many are there?
Well, you want to call them lines, don't you?
You could call them lines. Once you get really good at thinking of finite set theory, it's like the degenerate version of projective.
That picture that you drew there.
Right. You do eventually want to call them lines, but that's sort of futuristic terminology. Only once you convince people that set theory is a form of projective geometry, well, everyone calls them lines. Yeah?
So it works 5 choose 2.
Yeah, so 5 choose 2. That's certainly a good name for it, even if you have no idea what 5 choose 2 is, equals, that is what What is it? Well, here I'll tell you what it is, you know already. It's 5 factorial over 2 factorial times 3 factorial. Probably a fancy name for something like 10 or 15 something. Probably more like 10. But we're combinatorics who don't actually care what the number is. Well, and sometimes we care a lot, but actually more interesting than that number 10 is this. So what we'd like to do, you see, is to categorify everything I just said. So, right, in other words, now we have a nice, people usually use 5 choose 2 to be the number of way 2-element subsets of a 5-element set. But it's better, pardon me, to just use 5 choose 2 to mean the collection of 2-element subsets of a 5-element set. So if you think of this as a set, which would mean like stripping off the cardinality symbol here, then how could you interpret this equation here? So what set is this? That's not easy enough to do. So what does what does division mean in the world of sets? Modding out by a group action, for example. Yeah. So are we doing that here? Well, yes. Okay, you're starting to. So what's 5 factorial? And what does it mean as a set? It's a group of permutations of a 5-element set. So this is a group, right? You're using 5 bang or 5 factorial to be a group of all permutations of 5. So this is a group. We're modding out. Well, I hope we're modding out by a subgroup. That would be awfully nice. That would make it comprehensible then. What does times mean? Well, we know what times means, both for sets and for groups, so that's fine. So hopefully, the group 5 factorial has a subgroup 2 factorial times 3 factorial, and when we mod out by that, we get this 10-element set. So what is that subgroup? In fact, it's true. What's this subgroup of 5 factorial?
Permutations across.
Permutations of various subsets.
Oh, pretty big. Which subset? Let's be nice and specific.
The
Transpositions across something else,
The
right?
5 factorial is the entire set.
5 factorial is all the permutations of all 5 of these guys. What's 2 factorial times 3 factorial? Right, permutations where these guys can get mixed and those guys can get mixed, but they can't mix with each other. So it's like, imagine like an extremely rigid class system where none of these lower class guys or whatnot mix with any of the upper class guys. You say permutations, but you just know that not only the lower class people would ever be allowed into the upper class.
So it's the stabilizer of some particular subset.
This subgroup here is the stabilizer of some particular 2-element subset. That's right. So that is a particular choice of 2-element subset in the 5-element set. That's right. So this is so this is sometimes called the Young subgroup associated to that Young type. It's the permutations of our set and 5 in this case, which preserve some structure. I guess Tim has brainwashed you into believing by now that every subgroup of a permutation group preserves some structure. What structure on the 5-element set does this preserve? Don't point. We're being recorded.
The diagram. The Young diagram.
It's not the Young diagram. What structure exactly?
The D flag.
The D flag. Yeah, the D flag. That's why I call it the D flag. So the D flag is precisely, a D flag on it is precisely a way of taking your 5 elements and sticking them in here in such a way where you don't care what order they are in each row. So this D flag on the 5-element set is exactly the same as this D flag. And in particular case, it's just a choice of a two-element subset of our five-element set. And so this subgroup here, so you're preserving that D flag. And so what we're doing here is we're taking a group of all permutations mod the ones that preserve the D flag, and we're getting a set of D flags. And that's because the permutations act transitively on the set of all D flags. So the stabilizer system is mod up of it, you get a set of D flags. Of course, if we're thinking about these as sets, we should say isomorphic instead of equal. Numbers of this equation here. So that's right. So that's what's going on there. So now let's try to do the Q case. So let's look at, this is going to take more work, but let's get ready for it here. So let's look at what the D flag on F to the 5 is, and count those. So first of all, what is a D flag on that's a two-dimensional subspace of F5. That's probably the way I do want to think about it right now, or if you prefer, you could call it a line in the projective space. F5. We'll come for it later, but probably the first one. FP4, sorry. So let's try to count those, and let's try to count them by copying what we did in the Q equals 1 case, the set theory case. So when we counted the D flags in the set theory case, we got the concept of a binomial coefficient. But we saw that a binomial coefficient really was a group modulo a subgroup. Categorifying. So let's try to think about it that way. So let's find some group that acts transitively on all the D flags in this D case here, right? And then find the subgroup that preserves the D flag, and then the quotient of the group by the subgroup will be the set of the D flags. Okay, that's the idea. So we're looking for the obvious group that's floating around that's acting on the set of all planes in five-dimensional space, set of all 2D subspaces in five-dimensional space, acting transitively on them. And then we're going to look for the subgroup of that stabilizes the plane, and we'll take the quotient. So what's the group that's acting, I mean, it could be different groups that are acting on the set of all these 2D subspaces of F5. But what's the group that we should use?
It's going to be a general linear group in this case?
Right, the general linear group, right? Before, in the set theory case, we used the group of all permutations of the set. Now we're going to use the group of all linear transformations of our vector space. So that is an analogy that I mentioned before. So we'll say, okay, so GL5, comma F acts transitively on the set of all two-dimensional subspaces of F5. That's what our flags are in this case. That's easy to see, right? I have some 2D subspace, I can take a basis for it. There'll be some linear transformation that will map that over to any other independent pair of vectors. Get over to any other 2D subspace, so that's easy to see. And the stabilizer subgroup. Well, that's what we've got to figure out. But you really have to talk about the stabilizer subgroup of some particular two-dimensional subspace. It doesn't really, the subgroups will be isomorphic regardless of what you pick. But let's just take a two-dimensional subspace. It consists of all vectors that look like that. Right? So all vectors that are anything up here, anything here, zeros after that. Okay, so this is a particular. I know it's a goofy notation, but this is a notation for a two-dimensional subspace of F5. It's all the vectors that look like that. Now we can cover up. Let's do a little square. That's what it is. So that's actually a good way to think about it, because what we're doing is we're looking for all the stable line is a subgroup of this particular subspace, right? It's going to be some group of matrices, some group of 5 by 5 matrices. It has the property that when you apply them to any vector of this form, you get another vector of that form. Not with the same numbers up top, of course, some numbers up top. So what matrices, when you multiply them by a vector like this, give you a vector that again looks like this. That's what the stabilizer subgroup is. So someone tell me what the first thing I should do with this good. I'll mark this line divided by the cross. Draw some vertical lines and horizontal lines. Where should I draw it? 2 over, and how many down? 2. Okay. So I should think about it with respect to this decomposition. So I should think of a little 2 by 2 block, 2 by 3, 3 by 2, 3 by 3. Okay. So what do we know about what these different blocks can be like? Like what can that one be like?
Any GL2?
I can just be anything. Anything in GL2 is allowed there. Any invertible matrix could go in there. It has to be invertible, because otherwise the whole matrix would not be invertible. You won't see that yet. But anything can go in there. Because just do the old yoga of waving the arms around like this. I can help your students how to do that. Yeah, okay. What about over here? Anything, now it's because when you go 0, 0, 0, it doesn't matter what's in there, it's just going to get killed anyway. Okay, what about over here?
Nothing.
Nothing? 0. Nothing, 0, and the 10. Okay, that's 3 choices of answers. It has to be have a property that when applied to this sort of vector, no matter what this vector is, you get a vector of this type. So if you think about it, you can put a 1 up there and 0 elsewhere. You can see, hey, there's stuff down here. It's just got to be zeros. Or else you get something here that's not 0. So that's, now what about this stuff? That can be anything as well. So this is the subgroup. It's our stabilizer subgroup. It's a subgroup of GL5 that consists of matrices that look like this. This kind of subgroup is called a parabolic subgroup. I'm not defining it in general, but I guess I can define it quite generally. It's a parabolic subgroup of GLN. That's just jargon for a subgroup that preserves a D flag. So for any n and any t, we use this jargon, parabolic subgroup for a subgroup that preserves a D flag, and they'll always look sort of like this. What does that mean? Use some other examples to see what I mean by sort of like that. Okay, but we're just doing this example here. Okay, so now what we need to do to count the D flags is what? What do we have to do to count the D flags? Just give me an overall strategy here.
What is the cardinality of GLN for everyone?
First we got to count GLN. Then we got to count the size of this thing. Then we got to divide it. To count the size of this thing, we're going to need to think more about GLN. That's right. So the very first thing we should do is count the size of GLN. Okay, so moving on over here. You don't see too many TV shows where the announcer says, okay, I'm walking over to the right now. Keep the camera on me here. Probably in very early days. What?
Jerry Springer.
He does that? Oh, just as a joke? No? Just highly unprofessional. So, that's right. So to count the set of D flags in this particular case, we're just going to count the size of GLN, and maybe now I want to remind, well, I can tell this right F, but I could write S of Q. That's the Q elements, build the Q elements. And then we're going to divide by the size of this subgroup. And that will give us our answer. Maybe before we start getting into the details of counting all these things, let's think a little bit about that subgroup and what it's like. So someone already mentioned that this matrix up here can be anything in GL2. So why does it have to, that's just saying it's anything, the determinant isn't zero. So why does the determinant of that little block up there have to be non-zero? Let's just make sure we understand.
Otherwise the whole determinant will become zero.
Yeah. There's somebody or other's formula that says, I don't know what it is actually. There's one famous formula right that if you have an upper triangular matrix, the determinant is just the product of the entries down the diagonal. So if any one of them were zero, it'd be gay. This is sort of a generalization of that, which says the only way the determinant of this matrix can be non-zero is the determinant of that one is non-zero and the determinant of that one is non-zero.
And this is the product.
And it's the product of the determinant of those two. That's what somebody wrote this for. That's right. Yeah, you don't even need to worry at all about that. Which is why. That's right. In terms of some obvious linear algebra thing. So in other words, this group here, at least as a set, it's the same thing as GL2, because you can put any verbal matrix in, times GL3, put any verbal matrix there, times anything here, which I'll just write as f to the 2 times 3, since I can't multiply. Yeah, that's right. So that's true as a set that this group is.
The large block has to be GL3 as well. Oh yeah, I'm sorry, that's what you just got them saying. Never mind.
Yeah, these have, right.
Yeah.
Let's see. Can you make this even nicer maybe and make this a description of the group structure? It's not just the Cartesian product as a group of these three groups, right? Because if you multiply two of these kind of things, these guys are messing around with these guys, stuff like that. So does anyone know how to, I hope it's true, but I think there's like something you could do to make this a little bit different.
The GL2 and GL3 is just a regular old direct product, right? Because those are sort of different.
Yeah, if you didn't have these guys around, if those are all zeros, you just have the ordinary Cartesian product or direct product of these groups. Right? So you've got that. This thing here is need a subgroup of this group here.
So you need to group those two together and make a semi-direct product that allows.
I think it's a semi-direct product. That's what I would guess. Right? You have this group here. These kind of guys can act on those kind of stuff.
Yeah, it's also a quotient group. The GL2 plus GL3 is also a quotient.
Okay, yeah. If you've got a subgroup, it's also a quotient group. You can get yourself a little kind of short attack sequence that has enough arrows pointing in all directions. Make it be a semi-direct product. You can just mod out by these things. Okay, that's just a bit of a digression, but we're really trying to categorify everything. You see, we want to be able to erase all these stupid cardinality symbols and have these equations become isomorphisms, and we'd like them to become isomorphisms of the best possible sense. So this set is isomorphic to this group, mod this group, which is isomorphic to this group, mod this group. We would really like to have a description of it as a group.
That's any part of it.
Sorry?
That's any part.
Yeah. Right. Sorry, that's sort of stuff. Yeah, Jim?
For a semi-direct product, you need the action of one group on another, and it's pretty visible there, I think.
So I guess the GL2s are act on these two. You can think of this as F2 directs on F3.
Tensor.
Oh, tensor.
Something like that.
Right. So you think of this thing as the space of linear maps from a two-dimensional vector space to a three-dimensional vector space. smaller bases. That's what that will make it do. And so then, in a space of maps from a two-dimensional vector space to a three-dimensional vector space, GL2 acts on the inputs before GL3 acts on the outputs. So there's a nice way to act on this space of maps. So you can make this all like really beautiful one. Forget that you were ever talking about matrices about it all. But we're just going to count these different things. So it's easy to count that because we know that our field has q elements. So this one q to the 6 elements. So the hard part, the only hard part, is to count these GLs. Sorry. So that's what we need to do. So what's the cardinality of GL and F? Where now maybe I'll come up and admit I can deal with Q elements. I think I'll slide over one more notch this time. So,
John, can I just complain about something?
sure.
Again, in the semi-direct product, the F2 times 3. I'd just like to clarify what group that is. I mean, it's the ones down the diagonal, and then it's got the 2 by 3 block. Is that right? That's
Just the group F2 times 3 by F by itself.
Yeah, that's what we mean when we say that we have a semi-direct product there.
That's right. Yeah, that's right. Yeah, that's right. So, okay, so how can we count invertible n by n matrices? So this is like one of those typical combinatoric things where you sort of build up the structure you're describing by saying, oh, first we pick one of these, and then pick one of these, or something like that. So you talk to Purvis communicating by sign language in the back row.
You look at column by column.
Okay, so I look at the first column. How many choices do I have?
Anything that's not 0.
Can't be 0, that's for sure, right? Any linearly independent vector.
Yes.
So I can pick any vector in f to the n, not 0, so there are q to the n minus one of them. But maybe I should even not decategorify yet. Right? Maybe I should just describe these choices. So first we choose any vector that's not 0 for the first column. Okay. Now what kind of choices do we get for our second column?
Anything not in the line.
I didn't choose.
Anything
you don't have to choose twice what I choose before. That would be enough to make the columns linearly dependent.
Anything not in the line, so that the determinant will remain non-zero.
Yeah, anything that wasn't in the one-dimensional space spanned by the first vector that I chose. So my second vector can be any vector minus the one-dimensional space spanned by the first vector that I chose.
That's funny, because I mean, that F isn't that well defined. It's like you're cheating a little bit.
Right. That's right. What we're doing here is we're pretending that a bundle is trivial. That is, so first I pick some vector, it gives me some one-dimensional subspace of this. Then for some reason I call that one-dimensional space F. But what the subspace is, well, it actually depends on what choice I made. There's no canonical isomorphism between that one-dimensional subspace and F. So, yeah, I'm cheating slightly, which is exactly like pretending that a bundle is trivial. It's not really trivial.
And it becomes less cheating.
Well, it's kind of
category.
GLN is actually a bundle over a bundle over a bundle over a bundle, where each new time you have a bundle of next choices over your previous choices. And it's twisted, it's a highly twisted bundle, but if you're just counting the set of points in it, you don't need to worry about that. That's right. So this should be like, in quotes, a twisted product. It's really a bundle. This is the base space. And for each point in this base space, we have a fiber, which is the set of choices that we can make having made that first choice. Right. So then it goes on, so my next one could be, my next column could be any vector not in the space spanned by the first two, which have to be two-dimensional, and so on. And then, very end here, you still have choices, careful count,
And minus one.
and minus one. So that's the cardinality of GLN. All these F's are F sub Q. Terrible. It doesn't matter, but anyway. So now we count, and that's very easy because the number of points in FQ is Q. So it just becomes Qn minus 1 times Qn minus Q times all the way on Qn minus Qn minus 1. So that's how many guys there are in GLN of F sub Q. Now, for various nefarious reasons, I would like to fiddle around with this formula a little bit, make it look more like other stuff that we've already thought about. So what is this supposed to remind you of?
N factorial.
Yeah, it's supposed to remind you of a q factorial. So a q factorial would be a very similar sort of thing. So it's something like this, right? So we're going to make a bunch of mistakes which we'll correct for later, right? So that should remind you of that. Well, then I'll have to correct by multiplying by the minus 1. This should remind me of what q factorial. This is the nth q factorial. See? We're not done. We have to make corrections. This is going to turn into this with some corrections. This is going to turn into what q factorial? Yeah, the n minus first q factorial. So right, we can write this over q minus 1, but times q. I'll do that part of the correction already. So that's that. These corrections here, these are going to have to be compensated for at the end. So we go down, down, down. So we get here, which is, this is just q to the n minus 1 times the first times q minus 1, which is going to give us the first q factorial. But we've been accumulating all these q minus 1s down at the bottom, and now at the end you're going to pay our debt. So how many q minus 1s are there in the denominator there?
N minus 1. No, N.
The big question in life, the only hard question in combinatorics is it n, or is it n minus 1, or is it n plus 1? If you do that, you'd all be combinatorics. Sorry? Yeah, one for each column, right? We have n columns here. Yeah, so there's one. So we get times q minus 1 to the n. That's right. So what we get is, so we've got all this grungy crud that we accumulated in our pursuit of trying to make things beautiful, but then we've got the beautiful part, which is a q factorial, right? So this is the first q integer, the second, and minus first, the n. So that's n q factorial. All those fractions. And then we've got q minus 1 to the n. And then we've got this other gunk, which is q to the n choose 2. So is that n choose 2, or is it n minus 1 choose 2? Let me just be very hesitant about it. Right, like that. So it's a triangle number in any event. And I think, so it's really n choose 2? Okay. I'll take your word for it. So 2 choose 1.
You choose 2.
2 choose 2.
Same as 1.
The same as 1, which is working. Okay, so this is, so okay, just because it's shorter.
Isn't it 2 choose 1 the same as?
No, I did.
Okay.
2 choose 1, but it had nothing to do with the problem. We're talking about choose 2. Okay. 2 choose 2 is 1, which is working out. So that's the kind of triangle that we're getting. Okay, so that's the cardinality of GLN. Okay, so now let's use that to count the defects in this case. So what do we get here? So the set of D flags on F5, i.e. the set of two-dimensional subspaces of F5, is going to be the cardinality, cardinality of GL5 divided by the cardinality of GL2 times the cardinality of GL3 times the cardinality of F to the 2 times 3. That's what we're getting. But now, we see that each of these cardinalities of GLN, this is something we compute, something we computed. So the cardinality of GL5 is 5 q factorial, that's q to the minus 1/5, that's q to the 5 choose 2. And then down in the denominator, we get the same kinds of things for GL2 and GL3. 2 q factorial, minus 1/2, 2 choose 2, 3 q factorial, minus 1/3, 3 choose 2, and this extra fudge factor, which is q to the 6. So that looks horrible, but it's actually not. So what's good about this?
Q minus 1, Q minus 1.
Yeah, the q minus 1's cancel, and you can see that that's always going to work that way, right? So here I'm talking about two-dimensional subspaces of a 5-dimensional space, but we're going to want to generalize in a minute. Let those numbers be arbitrary, and so we need to know what's a coincidence and what's not. It's not a coincidence that this 2 plus this 3 is equal to that 5, and so all that stuff cancels. That's always going to be like that. And so that's good. And so we're left with, first of all, the stuff involving q factorials.
One of them is a 2.
Second of all, this slightly more mysterious stuff involving this power of the cube. Okay, let's first look at the first stuff, because that's by playing pleasant to the eye. So what does this first bunch of gunk deserve to be called?
Q, 1, 5, 2, 5, Q, 2, Q multiplied
5 q's to q, or a q-binomial coefficient. Yeah. So this is still by binomial coefficient, but with the factorials being replaced by q factorials. So people call it a q-binomial coefficient. It's a little q out there. So that's good, because there we see quite clearly that the kind of combinatorics we were doing for counting two-element sets is just getting q-deformed into counting the two-dimensional subspace. Then there's this horrible thing. Well, let's just think a little bit about that thing. So the way that I was thinking, well, let's see. Maybe someone's really smart, so I already know it. What's this equal to? 1. Okay, good. So it's just 1, really. But I was more slow-witted about it, so I wanted to see why it was 1. And so in my notes, I didn't actually write 5 choose 2. I just wrote some little symbol that meant you draw kind of triangle. It's a triangle number, as I said, but it's a triangle number which is a smaller triangle number. So in other words, you draw 5 by 5 square, but don't include the guys on the diagonal, so it's just 4 plus 3.
You draw two smaller, you draw two lines, you draw the same partition that you did.
You're saying I just drew this thing?
And I'm saying you should draw the triangle and then draw the same partition that.
Draw it like this? Yeah, right. Draw it just like I drew over there.
Do the block partition.
Not quite the same, is it?
It
It's
is-
very
it
related.
is the same.
Yeah, well, something about it is the same, that's for sure. Yeah, okay, so you're.
It's
drawing
simultaneous.
something.
Yeah, and then cut out half the triangle. Cut out half.
These guys are dead.
That's it.
Yeah, I claim that's the proof. So what's the idea? So this is
2 choose.
2 choose 2. This is 3 choose 2. This whole thing is 5 choose 2. And this upper rectangle here is Q6. So the fact that this number is equal to 1 is just saying that 5 choose 2 is equal to 2 choose 2 plus 3 choose 2 plus 2 times 3.
Why not
Well, you have to just get yourself started. Right? So 5 choose 2 is 10. Right? And 10 is 1 plus 2 plus 3 plus 4. So these particular blah choose 2 numbers are triangle numbers.
5 choose 2 is the number of choices you can make of 2 points, right? So either x, y, or y, x. So you choose only one of the two triangles, not x, y, and y.
Right,
And x
exactly.
is not y, so you exclude the diagonal.
Right, that's what's correct. So
That's what
a point in this grid would be a ordered pair in the 5-element set. Well, we want ordered pairs with distinct coordinates, so we don't count the ones with the diagonals, and we don't care about the ordinate, but the upper triangular part. So this here, the picture of the number of ways to pick the 2-element subset out of the 5-element set. And there are different ways to do it. You can pick them both in this 2-element part, you can pick them both in this 3-element part, or you can pick one from the 2 and one from the 3. Those are the different choices, so that's why you choose. That's why we're just saying, choose. Giving a proof, a picture proof. So that all cancels out. Okay, so the moral of the story is that if you're trying to count subspaces of a bigger dimensional vector space, you just use these q-binomial coefficients. What do you call the thing of all blah-dimensional subspaces of a Lie-dimensional vector space?
It's a log Grassmannian.
It's a Grassmannian, yeah. So if in general, if you have D being any uncombed Young diagram that just has 2 rows, so say, I don't know,
K.
say what?
A.
K, but wasn't I using K somewhere else? I was somewhere. I was using it to mean the number of rows. Yeah, I did. I'm going to call it L. So L and minus L by the number of boxes in these 2 rows. So then a D flag on S to the N. Sorry. A set of all D flags on S to the N. It's called the Grassmannian. Of, I don't know, of L-dimensional subspaces of S to the N. That's what it is. A collection of L-dimensional subspaces of S to the N. It's called Grassmannian. Sometimes people call it N, L. but I claim we have a better name for it now. So what does it really deserve to
And
be
choose
called?
LQ.
N choose L, but it's q-deform. Well, we probably shouldn't even call it Q. What should you really call it? F, right? Because F
Oh,
is
that's
the thing that there are Q.
Categorifying.
Yeah, I'm just being cute here, right? So in other words, instead of writing the number of elements in the field down here, I actually write the field. I don't know if application will ever pay off, but the point, trying to point out this in common parts, you've got all these numerical parameters floating around, but they're using names of various kind of sets. Okay, so we've described F binomial coefficients, and they're just Grassmannian. Okay, so now let's go and do the general case. I think we're now ready to count any sort of. So now just let D be any old uncombed Young diagram. So it just has all these. But I think nonetheless I'll use the method of the randomly chosen example. So the method of the randomly chosen example, right, is you pick a specific randomly chosen example and do the calculation for that example. The chances of getting the right answer if your method is wrong are infinitesimal. So it almost is a proof of the general case. In fact, this is apparently how Chinese mathematics worked before the Western civilization came along. People complain that Chinese mathematics doesn't have proofs. What they do instead is give algorithms for how to calculate things. And the algorithms are never described in general. They're always done in an example. And so for a long time, people thought that meant that these people were idiots because they didn't understand the idea of generality. But I think
the same thing about Babylon and Egypt.
I don't know much enough about that. My wife works a bit on Chinese mathematics. I know some discussions of that. So we're going back to Chinese mathematics here. So we're gonna call this. Right. So this is a general Young diagram, which has 2 boxes in the first row, 3 in the second, and 1 in the third. But we'll see instantly when we're done counting the D flags with this group. We'll see how we're really good at that. Yeah.
Does she also do green plastic?
She studies a little bit about it, yeah, in comparison to Chinese math. Okay, so here, N1, well, that's what N1, N2, and N3 are, the 3 rows of our Young diagram, and then N is some of these things. So it's 6. Okay, so we're going to first count D flags on a 6-element set. Maybe we will just understand the set of D flags. No, I'm sorry. So what I want you to do is to figure out how to count these things, but figure out how to count it using the fact that we've already understand the Grassmannian example. Or in set theory case, we already know all about binomial coefficients. So I know all about how to, how many ways there are to pick some number of things out of some larger number of things. And I want to use that building block to solve this harder problem here. So here you see, what is this? I've got a 6-element set. I'm trying to count all the ways to color 2 of the elements red, 3 of the elements blue, and 1 green.
Where we do we're going to first take 6, choose 2.
Okay, so 6 choose 2 is the first thing. That is, first I have to pick which of my 6 elements are going to be painted red. That is, are going to live in this subset.
And then we take the remaining 4 elements and choose 3.
Right. So then there are 4 left. And of those 4, 3 of them will get to be, where I said that was blue. Yeah, that's right. So Right, so then we can think about this a bit further and make it more beautiful. So it's a 6 factorial over 2 factorial times 3 factorial. And here, it's 4, huh? And so here I really mean this group mod this.
Not yet.
What?
No,
I'm just doing that.
No.
Yeah, I'm going much slower than you are. And then here we have 4 factorial over 3 factorial times 1 factorial. And then we say, hey, look, the 4 factorials cancel. And so it's really 6 factorial over 2 factorial times 3 factorial times 1 factorial. And that's just a better way to write the final answer because you can just see, hey, that's 2, 3, and 1. That's exactly this 2, 3, and 1 here. Well, or at least that's true if this example isn't fooling us somehow, into guessing a pattern that's not really there. But the pattern really is there. What's the real significance of what's going on here? Why are we really taking 6 factorial and dividing it by this product of factorials to count?
It's the same issue, it's like the order, well, I'm going to get pairs with order. Yeah, unordered pairs is different.
Unordered pairs?
We could commute between the first element, we commute the element, we commute that one element.
It's the subgroup that
Yeah.
looks at the
That's right.
young subgroup.
Yeah, so 6 factorial is a group of all permutations of 6, or 6 elements. This is the subgroup of permutations that fix a particular D flag. That is, that fix a particular way of dividing 6 element set into a 2 element set, 3 and 1. And so the group mod of the stabilizer gives the homogeneous space, the space homogeneous max transfer. So this is the young subgroup here. Preserving our D flag. So then, that I hope you see that there's nothing at all particular about the number of rows in this diagram or how long they are. It's just a very general thing. So you see, in general, the number, well, the set of D flags on an n-element set, it's just going to be n factorial over the product of the factorials. 1 factorial on up to nk factorial, where n1 up to nk was the number of dots, number of boxes in the rows of our Venn diagram. Okay. What's this kind of number called? Or what should it be
A
called?
multinomial
This is the case for what it is called is what it should be called. It should be called a multinomial coefficient, and it is called a multinomial coefficient. So that's the generalization of binomial coefficients. Get here. How should it be notated? I think I may remember how it is notated.
It's like a banana.
Is it really?
But you write all the terms, not
Right, right. So
all
for
the
some
forms.
reason, it's like how you really should have written the binomial
Yeah.
coefficient.
Common.
You've been even-handed, right? So the binomial coefficient, you're dividing your set into 2 subsets, but for some stupid reason you put the first one down there, and you say, well, then you know the second one is something very unfair. But here, we label how many elements there are in each of the k different subsets that add up to our n element set. So that's, I think, what it is.
Probably want to be common. So it's fine now, but when people write them.
I don't know what people normally do. I was
With
just trying
specific
to-
numbers, you won't, like, you don't want to write 6 to 321.
Right. Okay. How close do 2 numbers have to get before they actually multiply? Union reaction. Press the goal. Multiply. So,
Or even worse, they just stick together and become 20 feet.
yeah,
Actually, that's what they do.
Done. Right. Press uranium together and just get really heavy uranium. Nothing happens. So-
Uneducated ones do that.
Right, so that's just multinomial coefficient. Okay. So now, so finally, how many D flags are there going to be on a vector space? So maybe I will still use the method of randomly chosen example. So think of my same particular dumb diagram D, and imagine I'm counting the D flags. So a D flag would be a two-dimensional subspace sitting inside a five-dimensional space sitting inside our six-dimensional space. And we want to imagine counting them. Really just imagine understanding the set of them. And we want to somehow copy what worked before in the set basically. So to get one of these little stories in common tell, to choose one of these things, you gotta first do this, then you gotta do that, then you gotta do that. So basically, you look like you know exactly, yeah?
Oh, I
I know exactly how it's gonna work. Oh, you're just being agreeable.
I just want to be just like this reduced block or.
Well, this is just like I did before, so let's do it. Just the same, just different. So, okay.
You look at force. You do this in your first thing.
You just put a big F down. That's easy.
That's brushing it. Brushing it. It's like a journey.
This is all complicated.
You did this in your previous lecture.
I didn't do exactly this. I did something like
In a very specific
I did a very tall, skinny.
Yeah.
But that I don't think is what you call the randomly chosen example, right?
The method was the same.
You might not have known that there was some. Come on.
First
This
you
is
choose a
kind of just
two-dimensional.
refusing to help me.
First you choose a two-dimensional subspace.
First I choose a two-dimensional subspace out of a what?
Out of six. That's six.
Out of a six-dimensional
The
subspace.
six used to
So I
substitute.
make, let's be super slick. So, okay, that's the Grassmannian. A two-dimensional subspaces in a six-dimensional space over the vector space. Sorry, over the field category. Okay, so we have that set
Now you
for our first choices. And then,
now you reduce it to projective geometry to lesser dimension in some sense.
so just tell me what I'm supposed to write.
Now you are supposed to write 4 choose 3.
Okay, so,
And the reason is because it's now in a quotient space, not in the original X division.
right, so we had six-dimensional space, we chose in a two-dimensional subspace, the quotient space is four-dimensional, and now we're picking three-dimensional subspace of that.
Because you're working with things containing the 2 dimensions, right?
So this
You
is
can put.
three, here's the five, sorry, the five mod. That was really awful to understand, but yes, so we're picking three-dimensional subspace out of this four-dimensional quotient space. And I could write times here, but again, this is one of the evil products that Jim is thinking about. It's really, we have this Grassmannian, and then we have this big space, which is a bundle over this Grassmannian, whose fiber, any of whose fibers is isomorphic to this. Now, having made this choice, you've got a set of choices isomorphic to this, not in any canonical way. So if you think about not finite fields, but fields like R and C, then Grassmannians are actually manifolds, and I'm saying that this manifold is going to be a bundle space with some flavor that sticks. But here we're just sort of counting things over finite fields, so we don't even really need to worry about it. Some kind of twisted product, but in terms of counting, it works just like an ordinary product. So we get 6 choose 2 q factorial. Q factorial. And then we can do the trick that Alex was getting us to do before, which is just to say, hey, you can expand out these q factorials and see that there's cancellation. You can probably see this cancellation even before you took the cardinality. Or a little bit more. Just cancellation I'm talking about is that. And so you get what Prasad suggested that you do all along, just jump straight to the final answer. So we're getting a multinomial coefficient over all the factorials have been replaced by q factorials. And so this deserves to be called a q multinomial coefficient. I guess probably people do call it that. And of course, calling it that, I'm going to disappear now from Scott. Calling it that suggests that we call our set of flags by some similar notation. So in other words, quite generally, it's called any n box on the Venn diagram. We do this kind of thing. You can look at the set space of D flags on F to the N, and it deserves to be called N multi-choose N1, N2, and K. So F. And then you make cardinalities. You get the multinomial coefficient. Q-binomial coefficient. So that's how it works. So the point is that a whole bunch of common parts is getting categorified and turning into projective. Yeah.
Two questions. One is just like the multinomial coefficients for q equals 1 are integers. Is there some reason or something we can say why these q coefficients are actually polynomials and not just rational functions? And
There are polynomials in Q, and there is definitely a good reason for that. And I guess I should say, that's right. I don't even know if they are Q integers. Slightly different.
I don't know.
Probably not. No, maybe. But they're definitely polynomials in Q as natural number coefficients. And I should say a little bit about that. That's right. So, yeah, I could have practically paid you to make that recipe because I was like forgetting what the next thing I was going to say was.
I have another question.
Oh, I'm going to make me forget. Let me answer this one
Yeah,
first, and then hopefully your next question will be like exactly the same thing that I talked about. So we sort of categorified and q-deformed the theory of binomial coefficients at the same time. And there's still a bit more to squeeze out of this idea. So the very simple idea really is that these q integers are projective geometry over a finite field. What the ordinary integers are to finite set theory. But we didn't really get everything out of that idea that we could. Because in fact, there's another formula for the q integers. There's just a nice way to simplify or complicate this formula here. 1 plus q plus, the hard part is to know when to stop. So plus q squared plus 1. Plus q to the n minus 1. So the total of n terms, that's why it says n minus 1. And
That's how it's there.
yeah. And so you check your sanity by saying, if I set Q equals 1, is it better be the ordinary integer? Or is it better be n terms? So this fact here, this also actually wants to be categorifying. So in other words, these are numbers, we should do the same thing with sets. So Q becomes the set F, or field, with Q elements. What is this set here? We talked about it. It's the set, the number of elements is this. But we talked about it.
What is the number of points that's the projective plane?
That's the projective.
Or projective space, I'm sorry.
It's projective n minus 1 space.
That's the n minus 1.
It's just a goofy notation for it. The point is, count how many points there are here to get this. We've already seen that that projective space is a quotient like this, right? So that's the part we've already talked about. But we've never, I don't think, talked about this. What's going on here? So in other words, if I take the projectivized version of an n-dimensional space, how can I chop it up into pieces that look like that?
How many zeros are there starting with?
Yeah, that's right. That's a sort of that's an algebraic way to say it. There's a, sorry, I mean, the curling my lip when I said it. There's a more nice geometrical way to say the exact same thing. So, for example, if I take FP3, that's the set of all lines through the origin in three-dimensional space, right? And if I take my standard coordinate system, some favorite coordinate.
That's the bad part of it. Both of them involve making separate results.
Right, this is all evil. You need to make it specific so it's good, but just like. So, so the point is that if I'm picking a line here, there's different possibilities. One possibility is that it just is the very first axis. So that's one possibility. Then the next possibility is that it's on the plane spanned by the first two axes, but it's not the first axis. So if it's on this plane but not this axis, it will intersect this line parallel to the line there. Right? So all the other lines in this plane correspond to points on a line. So there's a line's worth of lines that lie on the plane spanned by the first two. F's worth of lines like that. Or it could be none of the above. So it could be a line that isn't on this plane. If we have a line that's not on this plane, it will actually poke up and it will intersect some plane parallel to this one. I'm just doing the same argument going up on one thing. Right, so there's a plane's worth of lines that don't lie on this plane. There's F2's worth of those. So that's a way to decompose this projective and way to decompose this projective plane into cells, they're called subsets. It illustrates the decomposition of the Q integer that we described.
What was the description of this before you started this one? Something about some zeros or something.
He was just saying that to describe a point in projective space, I need to give a vector but modulo scalar multiplication. And those vectors, So that vector will have some initial bunch of zeros and then a bunch of other crud. Or I guess actually the way we're describing it now is it's a bunch of crud and then a bunch of zeros at the end. And so the number of zeros there is what's going on for it. So this first line here, its second and its third coordinates were both zeros, one time.
Right.
Then these guys, just their third coordinate is zero. And then the generic lines that I hook up, none of their coordinates are zero. So you're getting,
I see.
you're getting a set of choices in each case, and they add up. So these are called Schubert cells.